Hello friends, welcome to the video lessons on electronic measuring instruments. In this class, I am going to discuss about AC bridges and the basic structure of an AC bridge, the condition for bridge balance for an AC bridge, and then we will try to analyze one such AC bridge, that is Maxwell bridge. And of course, what are the limitations of Maxwell bridge and how Maxwell bridge can be used for the measurement of unknown inductance. Before we go to the present topic, let us recollect what we have seen in the last class. In the last class, we have seen about what is a bridge circuit, how its basic structure would be, and what are the conditions for bridge balance, and what is the classification of bridge circuit, what is a Wheatstone bridge, and what for it is used. So basically a bridge circuit is a circuit consisting of four arms, and these four arms may consist of resistive elements or reactive elements or combination of both resistive and reactive elements. In addition to that, transducers can also be used in bridge circuits as one of the arms. Based on the type of elements used in the bridge arms, they are classified as DC bridges and AC bridges. DC bridges consist of only resistive bridge elements, and AC bridges consist of both resistive and reactive or combination of circuit elements. In a DC bridge, either DC or AC supply can be used as input excitation, whereas in case of AC bridge, only AC supply has to be used as excitation. In DC bridge, a null detector or a speaker or a headphone can be used at the output terminals for checking the bridge balance, and even in AC bridge also for checking the bridge balance, either a null detector or speaker or headset can be used. Then, after analyzing the condition for bridge balance, when a bridge is said to be balanced, the output at the bridge should be 0. So when the output at the bridge circuit is 0, then looking into the basic configuration of the bridge circuit, and after analyzing the circuit, we arrived at the conclusion that Z1, Z4 equal to Z2, Z3, or in other words, the product of the impedances of the opposite arms should be equal. And for measurement of resistance, a Wheatstone bridge is used, and we have seen the basic circuit of a Wheatstone bridge. It consists of, basically it is a DC bridge. It consists of only resistive circuit elements. In order to find the unknown resistance, It is placed as the fourth arm in the bridge, and the bridge is balanced by using a potentiometer in third arm, and by applying the condition for bridge balance, that is R1 Rx equal to R2 R3, we can find out the value of unknown resistance Rx as Rx is equal to R2 R3 by R1. Till that we have seen in the last class. Now, let us see what is an AC circuit, AC bridge circuit. AC bridge circuit mainly consists of impedances, which are combinations of both resistive and reactive elements. And only AC excitation has to be used, and a set of speakers or headsets or a null detector can be used at the output of the bridge for testing the bridge balance condition. AC bridges are mainly used for the measurement of inductance, capacitance, and frequency. For the measurement of inductance, variety of bridge circuits have been developed. Some of the bridge circuits among them are Maxwell bridge, Hay bridge, Anderson bridge, and Owen bridge. All these bridge circuits are used for the measurement of inductance. And some other bridge circuits used for the measurement of capacitance are De-Sauty bridge and sharing bridge. The basic circuit of an AC bridge circuit is the same as the DC bridge circuit. It consists of four bridge arms, a source of excitation, and a null detector. The power source supplies an AC voltage to the bridge at the desired frequency. In AC bridge circuit, each of the four arms is impedance. That means it consists of both resistance as well as reactance, and these are vector quantities. We use AC source in the place of battery. For DC applications, that means in DC bridges, a battery can be used as the source of EMF, whereas in case of AC bridges, AC source derived from the supply mains is used as excitation. A detector sensitive to small alternating potential is used to find the bridge balance condition. For measurement at low frequencies, the power line may act as the source of supply to the bridge. Power line frequency is 50 Hz. For high frequencies, electronic oscillators are used as bridge source supplies. The detectors used for AC bridges are first headphones. These are widely used as detectors at frequencies 250 Hz up to 3 or 4 kHz. They are most sensitive detectors for this range of frequencies. The next one is vibration galvanometer. A vibration galvanometer is extensively used for power and low audio frequency ranges, that is 50 Hz and below. These work at frequencies ranging from 5 Hz to 1000 Hz. The vibration galvanometers are used for power frequency range and low frequency range of audible frequency. The power frequency range is 50 Hz and low audio frequency range is 20 Hz to 200 kHz. As these instruments are very sensitive and selective for this frequency range. And the third one and the most important type of detector is tunable amplifier. A transistor amplifier can be tuned electrically to any desired frequency and then it can be made to respond to a narrow bandwidth at the bridge frequency. Tunable amplifier detects frequencies in the range of 10 Hz to 100 kilohertz. The schematic arrangement of an AC bridge circuit is shown here. And we know that the excitation is connected between terminals A and C, and the detector is connected between terminals B and D, and the impedances in the corresponding bridge arms are Z1 between A and B, Z2 between B and C, Z3 between A and D, Z4 between C and D. Now, the voltage drop from A to B equals to the voltage drop from A to D in magnitude and phase. So, in complex notation, it is given as E1 is equal to E2. That means I1 Z1. What is E1? E1 is nothing but the drop across the impedance Z1. So, it is I1 Z1. What is E2? E2 is nothing but the drop across the impedance Z2. So, it is I2 Z2. And the expression for I1 can be taken as E by Z1 plus Z3. This already we have seen in the last class also. Just as a part for recollection, we are once again looking at the analysis of the circuit. I2 is equal to I4, that is E by Z2 plus Z4. And substituting the values of I1 and I2 from equations 2 and 3 in equation 1, we arrive at the bridge balance condition, which is Z1 Z4 equal to Z2 Z3. The same bridge balance condition can also be written in terms of admittances as Y1 Y4 equal to Y2 Y3. If the impedance is written in the form of Z equal to magnitude of Z at an angle of theta, where Z represents the magnitude and theta represents the phase angle of the complex impedance, then we can rewrite the equation for bridge balance as modulus of Z1 at an angle theta 1 multiplied with modulus of Z4 at an angle theta 4 is equal to modulus of Z2 at an angle theta 2 multiplied with modulus of Z3 at an angle theta 3. So here magnitudes are to be multiplied and phase angles are to be summed up. So separating the magnitudes and phase angles, the condition for bridge balance is Z1 Z4 is equal to Z2 Z3 and theta 1 theta 4 sorry, theta 1 plus theta 4 is equal to theta 2 plus theta 3. So, in case of an AC bridge, the bridge balance requires to satisfy two conditions. The first condition is the product of the magnitudes of impedances of the opposite arms must be equal. That is, Z1, Z4 should be equal to Z2, Z3. The second condition is the sum of the phase angles of impedances in the opposite arms must be equal. That is, theta 1 plus theta 4 is equal to theta 2 plus theta 3. It is not necessary for the four impedances to have identical phase angles, or even for the impedances to be of the same kind. So as the phase angle differences satisfy the above condition. So that is about general introduction of an AC bridge. Now let us try to look into the details of an AC bridge used for the measurement of inductance, unknown inductance. That is Maxwell bridge. Maxwell bridge is an AC bridge, and it is used to measure unknown inductance in terms of known capacitance. One of the ratio arms has a resistance and a capacitance in parallel. The other ratio arm has fixed resistance R2. The third arm has variable resistance R3 for balancing the bridge, and the final arm is the unknown inductance. So the circuit for Maxwell bridge would be something like this. First arm consisting of a variable resistance in parallel with capacitance C1. Second arm is resistance R2. Third arm is resistance R3, and it is variable in order to balance the bridge. And the fourth arm is the unknown inductance, having a value of Lx and associated resistance Rx. An AC excitation E is applied across two terminals, and a detector is connected across the other two terminals. For balancing the Maxwell bridge, first R3 has to be adjusted for inductive balance. That is, first this resistance R3 has to be balanced for inductive balance. Then R1 has to be adjusted for capacitive balance. This process has to be repeated 3 to 4 times to achieve bridge balance. That is, first R3 has to be adjusted. So detector tends to come closer to null position. It will not be exactly 0. Then gradually adjust R1 for capacitive balance. The detector starts coming closer to the 0. Repeat this combination. Adjust R3, then adjust R1. Then adjust R3, then adjust R1. If we do this process continuously for 3 to 4 times, the bridge gets balanced and the detector shows zero current. At that condition, that is where the bridge is balanced, we know the equation, that is Z1 Z4 is equal to Z2 Z3. Here, in place of Z1, where in Z1 parallel combination of resistance and capacitance is used. So it would be better, instead of using impedance, if we choose admittance for calculating the unknown inductance values. So the condition for bridge balance Z1 Z4 equal to Z2 Z3 can be rewritten as Zx by Y1 is equal to Z2 Z3, or simply Zx is equal to Z2 Z3 Y1. And what is Zx? Rx plus j omega Lx. Z2 is R2, Z3 is R3, Y1 is 1 by R1 plus j omega C1. Let us substitute those values here in the equation. Y1 is 1 by R1 plus j omega C1, Z2 is R2, Z3 is R3, and Z is equal to Rx plus j omega Lx. So Rx plus j omega Lx is equal to R2 R3 into 1 by R1 plus j omega C1. Now here let me separate the two components, that is real and imaginary components, in the expression for Zx. So Rx plus j omega Lx can be written as R2 R3 by R1 plus j omega R2 R3 C1. Now separating the real and imaginary parts, we can write Rx as R2 R3 by R1 and Lx is equal to R2 R3 C1. These are the expressions for the unknown inductance value Rx plus j omega x. Values are Rx is R2 R3 by R1 and Lx is equal to R2 R3 C1. Then coming to advantages and disadvantages of Maxwell bridge. Main advantages with Maxwell bridge are: the measurement is independent of excitation frequency. The measurement is independent of excitation frequency. We have seen in the expressions for Rx or Lx, there is no term called omega. If any one of the terms for Rx or Cx consists of omega, then it would be difficult to calculate the value of either Rx or Cx, because it would be dependent on frequency, and frequency is variable. So using Maxwell bridge, main advantage is the measurement is independent of excitation frequency. And similarly, the bridge balance equation is independent of losses associated with inductance. The bridge balance equation is independent of losses associated with inductance. Third one, the Maxwell bridge is very useful for measurement of wide range of inductance at power and audio frequency. At power line frequencies, two audio frequencies, that is 50 hertz power line frequency, 20 hertz to 20 kilohertz is the audio frequency. So up to that frequencies, Maxwell bridge can be used comfortably for the measurement of unknown inductance, either or the unknown frequency. But the main drawback with Maxwell bridge is it is not suitable for the measurement of inductance values having quality factors which are very low or which are very high. Maxwell bridge can be used for inductance measurements only for inductances having a quality factor of greater than 1 and less than 10. What is quality factor? Quality factor is omega L by R. The higher the value of inductance when compared with the value of associated resistance, the better would be the quality factor of the coil. So here for Maxwell bridge, it can be used for the measurement of inductance for coils having a quality factor greater than 1 and less than 10. Second condition, the bridge balance equations are independent of frequency, ideally, but practically the properties of coil under test they will vary with frequency, which can cause some errors. This is the drawback with Maxwell's bridge. And let us try to solve one example problem wherein the bridge arms are given as R1 is equal to 235 kilo ohms, C1 is equal to 0.012 microfarads, R2 is equal to 2.5 kilo ohms, and R3 is equal to 50 kilo ohms. We have to find out the unknown impedance. We know that unknown impedance is Rx plus j omega Lx, and the expression for Rx is R2 R3 by R1. So R2 is 2.5 kilo ohms, that is 2.5 into 10 power 3. R3 is 50 kilo ohms, that is 50 into 10 power 3, divided by R1 is 235 kilo ohms, that is 235 into 10 power 3. In numerator it is 10 power 6 and denominator it is 10 power 3. So put together it would be 10 power 3 in the numerator, and the value is 2.5 into 50 by 235. If you calculate, it comes around 0.0532 kilo ohms, or in other words 532 ohms. And the expression for unknown inductance Lx is equal to R2 R3 C1. R2 is 2.5 into 10 power 3, R3 is 50 into 10 power 3, and C1 is 0.012 into 10 power minus 6. Here 10 power 3 into 10 power 3 into 10 power minus 6 get cancelled out. So the remaining term is 2.5 into 50 into 0.012. If you do the calculation, it comes out to be 1.5. So the unknown inductance is 1.5 Henry, and the associated resistance is 532 ohms. Yes, this is all about Maxwell bridge. In a moment, we'll see another AC bridge, that is sharing bridge, and we will try to analyze the circuit. Stay connected.